Here we're going to look at other examples of sequences defined by recursion. And we'll see what that means in just a moment. Remember that Fibonacci's sequence is specified by two base cases. We say what the first two values are, and then we give something called a recursive formula that tells us how to compute all the others. Well, many interesting sequences can be described in a similar way, and to give you some feeling for all the different kinds of things you might be able to do with this idea of recursion, I'm going to give you a series of examples. So here's my first one. Here, I'm going to start just by showing you a few terms of the sequence and see if you're getting the same idea that I have in mind when I wrote it down. So here's how it starts out. 9, 16, 23, 30, 37, 44. Now you're probably getting impatient with me and thinking, why are you saying this so slowly? I know what you're doing. All you're doing to get the next term from the previous one is adding 7. That's right. That's what I'm doing. Okay? This is an example of what's called an arithmetic sequence. And the recursive formula for this particular arithmetic sequence is an equals an minus 1 plus 7, which is just a fancy way of saying to get a term of the sequence, take the previous term and add 7. Now, you can't start out with that rule because there is no previous term. So it's not enough just to give the recursive formula. You also need to give a little bit of extra information. Here it's just one value. You have to say a1 is equal to 9. So here we say there's just one base case, unlike in the Fibonacci sequence where we had to give two base cases. Now, what do I mean by saying it's an arithmetic sequence? Well, this is a sequence in which you always get from one term to the next by adding a fixed number. We're going to look at another slide that explains that in more detail. I want to note before I go there that I seem to be mispronouncing this word, but I'm not. Okay, it looks like the word arithmetic, but I'm using it as an adjective, and therefore I pronounce it this funny way, arithmetic. What is an arithmetic sequence in general? Well, as I've said, an arithmetic sequence is one in which the recursive formula simply says to get the nth term from the n minus first term, add a fixed number. We're going to call this number d when we talk about it. And it's called the common difference. Notice in the previous example, which I'll go back to, that the value of d was 7. Okay, more generally, it can be any fixed number. Now, you might wonder, why do I call it the common difference? Because after all, we're adding it on. Where's the subtraction? Well, the point is, if I give you a little bit of the sequence, as I did in this example, how would you compute the value of d? You would subtract, right? Because it's the difference between any pair of consecutive terms. For example, consider 23 and 30. If you subtract 30 minus 23, you get 7, exactly the number you said was the common difference. All right, that's arithmetic sequences. Let's go on now to another type called geometric sequences. This time I'm going to give you an application where geometric sequences arise. Suppose that you invest $1,000 in a bank account, which is paying 5% annual interest with annual compounding. Now, to say you get compounding is to say you get interest on your interest. Now, let's ask ourselves, how much will we have at the end of 1 year? Well, since it's 5% interest and we're just doing annual compounding, we're not doing daily or monthly compounding, you can just say, well, at the end of the year, I get 5% of my $1,000. That's $50. That's my interest. Of course, I also get to keep the original amount, $1,000. So the total is $1,050. Now, there's an alternative way to do that calculation, and it's actually going to be the way we're going to think about doing this calculation. Instead of saying take 5% of 1,000 and then add it to 1,000, why don't we just say take 105% of 1,000. In other words, let's multiply by 1.05. Right? If you know how much you put in the bank at the beginning, then a year later, just multiply that by 1.05. Okay, and then you can easily go on to the end of 2 years or 3 years or 4 years. All you ever do is you take the amount at the end of the previous year and you multiply it by 1.05. Right? We took 1,000, we multiplied it by 1.05. That gave us the amount 1,050. Now we take 1,050, we multiply by 1.05. That gives us 1,102.50. And so I continue on in that same way, always multiplying by 1.05. This is said to be a geometric sequence. If I take the amounts that I have in the bank, starting with the 1,000 I started with, write that as a sequence. This is a geometric sequence. This is a sequence in which you obtain every term from the previous term by multiplying by a certain number. Okay? In an arithmetic sequence, we were always adding the same amount. In a geometric sequence, we're always multiplying by the same amount. Now this amount that we're multiplying by, in this context, we're going to denote it by R, and we'll call it the common ratio. Again, it might seem odd to call it the common ratio, which suggests division rather than multiplication, but it's easy enough to explain. Namely, take any two consecutive numbers in the sequence and divide one by the other. Divide, for example, 1,050 by 1,000, and you'll recover 1.05. That's the common ratio. All right, let's go on to other examples. Now, these are not large classes of examples like arithmetic sequences and geometric sequences. These are just single examples, and they don't have any special names. I'm going to call the terms of this sequence B1, B2, B3, and so on. And to begin with, let me tell you three base cases. Let me tell you that the first three terms, B1, B2, and B3, are all 1. And then the recursive formula says Bn equals Bn minus 3 plus Bn minus 2. You can't use that formula when n is 1, 2, or 3. You can start using it when n is 4. That is to say, to calculate the fourth term of the sequence. And I'm going to demonstrate how I do this calculation. I'm going to go away from the slides for a moment. All right, we're looking at the same definition again. I'm telling you B1 and B2 and B3 are all 1, and I'm giving you that same recursive formula, Bn equals Bn minus 3 plus Bn minus 2. Now, we know B1, we know B2, we know B3, so what's B4? Well, take the formula above, the recursive formula, and replace n by 4. Now, I will do that exactly as I've said. I will replace n by 4 everywhere that I see it. Notice that it occurs in 3 different places. And that's what we get. B4 equals B4 minus 3 plus B4 minus 2. But those subscripts are just numbers, which we can work out. 4 minus 3 is 1, and 4 minus 2 is 2. So we've learned that B4 is B1 plus B2. Okay, but those we know, B1 is 1, and B2 is 1. And I add them together, and I get 2. So B4 is 2. Okay, what about B5? Here I'm going to do it a little more quickly. I realize if n is 5, then the subscript n minus 3 must be 2. Notice I did a little bit of arithmetic just verbally, and I got B2. Okay, and then B what? Well, if n is 5, then n minus 2 must be 3. So B2 plus B3. B5 is B2 plus B3. Okay, B2, what was B2? That was 1. And B3 was 1. And when I add them together, I get 2. Okay, similarly, what's B6? B6 must be B3 plus B4. B3 was 1. Wait a minute, what's B4? And now we realize, of course, we need to use the result of an earlier calculation. B4 was 2, so we learn that B6 is 3. B7 must be B4 plus b5. b4 we calculated to be 2. b5 was also 2, so we get here 4. And one more before I stop. b8 is b5 plus b6. b5 was 2. b6 was 3, and so we get 5. Okay, b8 is 5. Now maybe it's time to try to get a more sophisticated understanding of what this is saying. Notice that this is not the type of equation that we saw when we were generating the Fibonacci sequence, because it doesn't say add the previous two terms. It doesn't say that bn is bn minus 2 plus bn minus 1. In fact, it never says anything about bn minus 1. What it's telling you is ignore the previous term, skip over it, and look at the two that come before that, right? You're looking back 3 steps and also 2 steps, never just 1 step back. So if you get that idea, let me show you how you can do this more quickly. We start with a 1, and then another 1, and another 1, 3 ones. Okay, and now what are we supposed to do? Well, cross off. Don't think about that 1 there. Think of the ones that are ahead of it. These 2. Add those together, they give you 2. All right, I'd like to know what comes next. Well, ignore the 2. Look at the 2 that come before that. It's a pair of 1s. Add them and you get a 2. Again, ignore the 1 that's immediately ahead. Add the 1 and the 2 and you get the 3. 2 plus 2 is 4. 2 plus 3 is 5. 3 plus 4 is 7. 4 plus 5 is 9. 5 plus 7 is 12. 7 plus 9 is 16, and so on. You could continue this, of course, as long as you like. All right, coming back to the slideshow, here is the sequence that we were generating, and I've shown you even a little further than I showed you in my own calculation. Let's go on to another example. I'm going to call the terms in this sequence C1, C2, C3, and so on. There's one base case. C1 is 3. And then we have this rather odd-looking rule that says when n is greater than or equal to 2, define Cn by using either one of 2 formulas. Of course, you need some way of determining which formula to use, and the way you do that is you look at the previous term, Cn minus 1, and you ask, is it even or is it odd? If the previous term is even, then you're supposed to multiply it by 1/2, that is to say, divide by 2. And if the previous term is odd, then don't divide by 2. Instead, multiply by 3 and add 1. Well, that's what I've just said, as you see down below. If the previous term is even, then divide it by 2. If the previous term is odd, multiply it by 3 and then add 1. All right, again, let's see how much of this we can generate. Oh, I didn't quite start the right way here. Let me quickly fix this up. We want to calculate C2 and then C3 and then C4 and C5 and C6. All right. Okay, so what's C2? Well, you have to look back at C1. C1 is 3. Is it even or is it odd? It's odd. So we need to use this formula right here that I'm boxing. In fact, let me copy it and paste it where I want it. And of course, the value that I'm using for n is 2, so this is C1. So C2 is 3C1 plus 1. That is 3 times 3. Let me use that symbol for multiplication, plus 1. Doing that indicated arithmetic, we get 10. Okay, what about C3? Well, look back at C2. Is it even? Is it odd? C2 is 10, which is even. So now we're supposed to use this other formula, which I'll copy and paste. We want to use this when n is 3, and therefore n minus 1 is 2. So it says 1/2 C2, so this is 1/2. Let me copy that from here. 1/2 times 10, which is 5. Okay, what is C4? Well, again, we have to ask, was the previous term odd or even? The answer is it was odd, and therefore we should say 3 times the previous term plus 1, and that gives us 16. And what about C5? Well, C4 was even, so we divide by 2, we get 8. And C5 is even, so C6 is 4. And C7 is 4 divided by 2, which is 2, and that's still even. So again, we divide by 2. That gives us 1. Okay, let's keep going. C9. Well, the previous thing is odd. So this time we don't divide by 2. We have to multiply by 3 and add 1, and that will give us 4. And then we get C10, which is 4 divided by 2. And at this point, you may suddenly realize, wait a minute, this is going to repeat forever. That is to say, the pattern of 3 numbers, 4, 2, 1, 4, 2, 1, will repeat forever. Right? When you reach 1, you're going to have to use the rule that says multiply by 3 and add 1. Then you'll divide by 2 to get 2. You divide by 2 again to get 1, and then you'll just repeat that whole process again. All right, so here I'm showing you what we generated, and I'm showing you that the 4, 2, 1 repeats forever. So we went 3, 10, 5, 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1. That block of 4, 2, 1 repeating forever. Now, what will happen if we change this example ever so slightly? Just change the first term. In other words, just change the base case from 3 to something else and keep that same recursive formula. And over on the right, I'm showing you various examples. If you start with 2, then you get repetition really from the very beginning. If you start with 5, you'll go 5, 16, 8, 4, 2, 1. You're already into the pattern. If you start with 7, it takes a little while longer, but pretty soon you come into that same pattern of 4, 2, 1, 4, 2, 1. Same thing if you start with 9. Now you can explore this on your own if you know how to build a spreadsheet to do this. In fact, let me show you a little spreadsheet that I made so that I could do this. And here's the spreadsheet. Now, I'm not going to expect that you actually know about building spreadsheets, especially one that has a formula like this, but I just want to point out we can mechanize this calculation. We can just ask a spreadsheet to do these very repetitive calculations for us. And here I have shown you the sequence that I showed you earlier. Now it's reading down in this column, 3, 10, 5, 16, and so on. And if I want to explore what happens if I try a different starting value, well, then I just stick in a different starting value. Instead of 3, let me type a 5. And immediately, when I hit return, it recalculates everything for me. Let me try 19. Okay, if I try 19, well, at the beginning, some haphazard looking values, but eventually it seems to very quickly come onto the same pattern. Let me try 27. Oh, wait a minute. Now I don't see this repetition of the 4, 2, 1. But let me just go further down in the sequence. Okay, lots of odd-looking numbers. Maybe it never happens that it goes into this 4, 2, 1 business. But yes, it does, okay? So right here, you hit the 4. That's the 110th term of the sequence. And now you begin going 4, 2, 1, 4, 2, 1. We now know this is going to have to repeat forever. So it's sort of amazing. You try various values here, and it seems like you always fall into this same pattern. So let me state that as a question. Suppose you take this sort of recursion, where we had this rule, and you take an arbitrary base case, an arbitrary starting value. Must the sequence always eventually become 4, 2, 1, repeating forever? And the answer to that is Nobody knows. No one knows the answer to that question. Anyone who has tried a few examples quickly becomes convinced this has to be true. But no one has been able to prove that this always happens. This is an unsolved problem in mathematics. All right, one last example in this lecture. Here I'm going to call the terms of the sequence D1, D2, D3, etc. And in the box, you can see my base case, just a single base case, D1 equals 1, and then a recursive formula that says Dn equals Dn minus 1 plus 2n minus 1. Again, I want to go away from the lecture slides and carefully work out a few values. Well, here we are. I've repeated the definition. D1 is 1. Dn equals Dn minus 1 plus 2n minus 1 when n is at least 2. All right. Again, I forgot to change some subscripts there. I want to calculate D2, D3, D4, D5, and so on. All right. What about D2? Okay, we employ the recursive formula, which says that D2 is D1 plus what number? Well, we're letting n be 2, right? So we want to add 2 times 2 minus 1. That's 3. So D2 is D1 plus 3. That's 1 plus 3 gives you 4. Okay, what about D3? Well, again, we're going to employ the recursive formula when n is 3 now. So this says D3 equals D2 plus what number? Don't say 3, because in fact, you don't want to be adding 3. It should be 2 times 3 minus 1. That's a 5. Okay, so D3 is D2 plus 5, and that is 4 plus 5, which is 9. D4 is D3 plus 11, which is 11. Why did I say 11? You can catch me on that one. Let me say that again. If n is 4, then 2n minus 1 is 2 times 4 minus 1. That's a 7. I shouldn't have said 11. So 9 plus 7, that's 16. And D5 is D4 plus now 9, which is 16 plus 9, which is 25. Let's do one more. And that is D6 is D5 plus now 11. And that is 25 plus 11, which is 36. So thus far the sequence goes 1, 4, 9, 16, 25, 36. And here I'm showing you what I got. 1, 4, 9, 16, 25, 36, 49, 64. I bet you look at that and say, wait a minute, I know something about those. Those are the perfect squares. In fact, it seems that what we're getting are exactly the perfect squares of n. That is to say, the first term is 1 squared, the second term is 2 squared, the third term is 3 squared, the fourth term is 4 squared, and so on. We haven't actually proved this. In fact, it's quite a bit of a challenge. How do you prove that what we've observed here really is true? But there are ways of proving it. Mathematicians know ways of proving things like this using something called mathematical induction. But let's not worry about that. What I want to point out is we started with a recursive definition for our sequence. That is to say, a definition that told us how to compute a term by looking at previous terms. But now it seems we've come up with what we would call an explicit formula. That is to say, a formula that would allow us to compute a term of the sequence without recursion, okay, without looking back at previous terms. Just to make it clear what the big difference is between these, suppose I gave you that definition in the box and I asked you to calculate D100, the 100th term of the sequence. You would find that a really tiresome task, and probably you'd get so tired you'd make a mistake and not get the correct value. On the other hand, if you recognize that dn is n squared, then it's an easy matter to say what the 100th term must be. It must be 100 squared, which is 10,000. Now, you shouldn't expect that you can always find an explicit formula. You're really very lucky when you discover an explicit formula for a sequence rather than a recursive formula. But if you can find one, it's certainly nice.